Hello friends, today we will study examples from exercise 2.2 of methods of real analysis by R.R. Goldberg. So take the first example. Let Sn be sequence convergent sequence. Let Sn be convergent sequence of real numbers such that limit of Sn is equal to L and Sn is less equal M for every n greater than for every n. Then so that L is less equal M. We'll prove that L less equal M. Solution. On contrary, suppose L is greater than M. On contrary, suppose L greater than M. Then epsilon is equal to mod of L minus or L minus M by 2 is greater than 0. Or we'll just take L minus M. Now since limit of Sn is equal to L, therefore for epsilon is equal to mod L minus M greater than 0. For any epsilon there is some positive integer. There exists positive integer n naught such that mod of Sn minus L is less than epsilon is equal to L minus M for any n greater equal to n naught. What this implies is mod of Sn minus L is less than L minus M. Therefore, L minus M minus L. Oh. Mod x minus a less than delta implies is a minus delta is less than x is less than a plus delta. Means L minus M is less than Sn is less than L plus L minus M. For any n greater equal n naught. Now we'll only take this part. So this L get cancelled and we'll get M is less than Sn for every n greater equal n naught. This is contradiction to Sn less equal M. This is contradiction to Sn less equal M for every n greater equal n naught. And therefore our assumption is wrong. Assumption is wrong. And therefore L must be less equal to M. So simple. So on parallel line, if I take the result, if Sn is convergent sequence of real numbers such that limit of Sn is equal to L and Sn is greater equal to M, this is say small m, for every n, then our limit must be greater equal to M. Must be greater equal M. See now changes here. On contrary, suppose L is less than M, then epsilon is equal to your M minus L is greater than 0. M minus L. We have to show that what I said here, and Sn greater equal M. Sn greater equal M. Then L is greater equal M. On contrary, suppose L is less than small m. Okay. Then your epsilon is equal to M minus L must be greater than 0. Must be greater than 0. epsilon is equal to m minus L here, m minus L is greater than 0 such that here we will get m minus L, right? By using this we will get here m minus L. See changes, m minus L. Now by comparing this with this, okay, this implies this side L get cancelled. So this implies Sn is less than m for every n greater equal n naught. This is contradiction to m is less equal m. M is less equal Sn for all n greater equal m. And therefore small m must be greater equal less equal m. Small m is less equal m. Is it clear? So by combining these two results, okay, if Sn is convergent sequence, real sequence, such that m is less equal, Sn less equal L, capital M for every n, and limit of Sn is equal to L, then so that m is less equal L less equal m. M less equal L less equal m. Is it clear? We can extend this result for two sequences. If I have two sequences Sn and say Tn, here Sn converges to L, Tn converges to m, and Sn is less equal Tn for all n, then limit of Sn must be less equal limit of Tn. Limit of Sn must be less equal limit of Tn. Okay, so note this point also. So here I am just taking exercises from R.R. Goldberg, so I am not taking other examples. Some examples I am adding. Next example, if I have two real numbers, okay, so let Lm belongs to R be such that L is less equal m plus epsilon for every epsilon greater than 0, then so that L is also less equal m. L is less equal m. Now we have given L is less equal m. L is less equal m. What that implies is, since L is less equal m plus epsilon for every epsilon greater than 0, therefore L minus m is less equal epsilon for every epsilon greater than 0. So if it is a negative number, then it is also less than that. Okay. So therefore, modulus of L minus m must be less equal epsilon for every epsilon greater than 0. Plus minus. If negative, it is less than that. If L minus m is positive, it is also less than that. Okay. So L minus m less equal epsilon, therefore mod of L minus m is less than epsilon. Okay. Okay, now what is our claim? L less equal m. If m is greater, L is greater than m, then epsilon is equal to mod of L minus m by 2 greater than 0. By hypothesis, mod L minus m is less equal mod of L minus m by 2. This is zero is less than mod L minus M less than this. This is impossible. This is impossible. Okay. As 0 less than a by 2 is impossible. For any real number, half of that real number must be less than 2. Okay. As 0 is less than a by 2 is less than a for any a greater than 0. This is true. Okay. And therefore, L must be equal to M. L is equal to M. Is it clear? So, if I assume that L is greater than M, L is greater than M, then we are getting contradiction. We are getting contradiction. Is it right? So, or L not equal to M. If I assume here L not equal to M, L not equal to M, then we are getting contradiction. Okay. Then epsilon is equal to mod L minus M by 2 greater than 0. Okay. So, this implies a claim, what is our, they show that L is precisely M. This is our aim. No. Okay. L is the less equal M. And that's why I assume that if L greater than M, so that is correct. Our aim is to show that L is less than equal to M. So if I assume that L is greater than M, then epsilon is equal to mod L minus M by 2 gives us contradiction. Okay. Now take the example. Find positive integer n naught such that positive integer n naught such that say mod of, if I take some term of sequence 2n upon n plus 3, then its limit as n goes to infinity, that is near to 2, is less than some epsilon fixed. So if I take say 1 by 5 for every n greater equal n naught. Also show that limit of 2n upon n plus 3 is equal to 2. Solution: mod of 2n upon n plus 3 minus 2. This is equal to, okay, 2n minus 6 upon n plus 3. 2n get cancelled, which is equal to 6 upon n plus 3. This is less equal 6 upon n naught plus 3 for every n greater equal n naught. U1 for this. Now 6 upon n naught plus 3 is less than 5, 1 by 5. If I take the cross multiplication, we will get n naught plus 3 is greater than 30, and therefore n naught is greater than 27. Okay, n naught plus 3 is greater than 30. This is equivalent to n naught is greater than 30 minus 3, that is 27. So I want positive integer n naught greater than 27. So from this there exists n naught is equal to 28 such that mod of 2n upon n plus 3 minus 2 is less than 1 by 5 for every n greater equal 28. For every n greater equal 28. Now, mod of, now for epsilon greater than 0, mod of or 6 upon n naught plus 3 is less equal 6 upon n naught is less than epsilon if and only n naught is greater than 6 upon epsilon. Okay, so this is 1, this is 2, and this is 3. So from 1 and 3, for epsilon greater than 0, for given epsilon greater than 0, there exists positive integer n naught greater than 6 by epsilon such that mod of 2n upon n plus 3 minus 2 is less than epsilon for any n greater or equal n naught, and that n naught is nothing but this. Therefore, limit n tends to infinity of 2n upon n plus 3 equal to 2. We'll take one more example of this type. For clearing the definition. Find n naught such that, find positive integer n naught such that 1 upon square root of n plus 1 is less than, say, 0.03 for every n greater or equal n naught. Also, so that limit of 1 upon square root of n plus 1 is 0. So solution, 1 upon root of n plus 1 is less equal 1 upon square root of n naught plus 1 or every n greater equal n naught. Since for n greater equal n naught, n plus 1 is greater equal n naught plus 1, the square roots also satisfies that, and in reciprocal we'll get this inequality. Okay. Now, so this is 1. Now, 1 upon square root of n naught plus 1, this is again less equal 1 upon root, or I will take, say, 0.03, which is equal to 3 upon 100. And therefore, by taking the square and reciprocal, n naught plus 1 is greater than 100 by 3 its square, which is nothing but 10,000 100 square upon 3 is nothing but 3 threes, remainder 1 3, remainder 1 3, 3.3, and so on and so on. Is it clear? Oh, sorry, what is the square of 3? That is 9. Okay, then we will get 1.11 and so on. Therefore, n naught is greater than 1110.11. From 1 and 2. From 1 and 2. So this from 1 and 2, 1 upon root of n plus 1 is less than equal to 0.03 for every n greater equal n naught. I want positive integer, so I'll take 1 1 1 1. I want n naught to be greater than this. What is next n naught? Positive integer greater than this real number, that is 1111. Is it clear? Now to show limit of n tends to infinity of 1 upon square root of n plus 1 is equal to 0. So for this, mod of 1 upon root of n plus 1 minus 0, which is same as 1 upon root of n plus 1, right, is less equal 1 upon root of n naught plus 1 is less equal 1 upon root n naught. For every n greater equal n naught. Okay. Now for epsilon greater than 0, 1 upon root n naught is less than epsilon if and only if n naught is greater than 1 upon epsilon square. 1 upon epsilon square. Okay. So from 1 and 2, from 1 and 2, for given epsilon greater than 0, there exists positive integer n naught greater than 1 upon epsilon square, such that mod of 1 upon root of n plus 1 minus 0 is less than epsilon for every n greater equal n naught. And therefore by definition, limit n tends to infinity of 1 upon square root n plus 1 is equal to 0. So thus, here we applied epsilon n naught definition to evaluate limit of sequence. We also taken some few examples of this type while discussing the convergence of limit of sequence. So with this discussion, in this session we have completed few examples from exercises. Try to solve the parallel examples of this type for your practice. You can write your equations on your own, you can judge their limits, you can apply this definition, you can choose particular epsilon like 1 by 5, 1 by 10, 11 by 15, etc. And for that also, what is your positive integer n naught in that case? Okay, to clear your definition of convergent sequence, limit of the sequence. So with this discussion, we'll stop here. Thanks for listening this session carefully. Bye bye.